Sponsored by Novium. What if I told you you can see inside of this rocket motor, or view the traces on this PCB? How would you know if this set of rocket fins had a good composite layup, or if this very expensive phenolic round was manufactured correctly? Whoa! Hi, I'm the Hamburglar, and you're watching Disney Channel. Hi, I'm Joe, a man with a music degree, the password to this YouTube channel, and a plane ticket to San Francisco. Way up north in the old Frisco, there's no way anyone calls it that. Up north in San Francisco is a company called Lumafield. They are not sponsoring this video, but they did agree to pay for the flight in the interest of transparency. Lumafield makes industrial CT scanners and the software that goes along with it. So I flew up north with a few PCBs, this massive phenolic round, which TSA did not love, and this set of rocket fins, which TSA loved even less. This is not an explainer on X-rays, but you can think of them like this. X-rays are able to shoot through most objects, but not before becoming attenuated a little bit. If we take this object, we put an X-ray emitter here, and then an X-ray detector here, we can get an image of the object. And then, if we take a fourth axis and we spin this object around, we can get a three-dimensional scan of the whole object. In this video, we're going to take a look at those scans, first comparing two different PCBs to each other, then we'll look at a single rocket motor, compare two rocket motors to each other, and finish out with a little bit of composite evaluation. There's tons of interesting detail here, and I want to give it the time it deserves. This video is a little slower and longer, but I hope you enjoy it. The first item we're looking at here is the very first circuit board I ever designed. This never flew on any rockets, but it was one of the pathfinders that led to the Signal PCB, which eventually became a commercial product. Here's the overview of the board, and I want to start by zooming in to the processor. In contrast to how this appears in real life, we can see right through the ceramic, which holds these little pins out the side. The actual processing unit sits in the middle of the ceramic here with these very small air wires that bridge out to each one of the leads. We can't really see that in this scan. You can scan for longer to get higher resolution data, and the Lumafield machines can actually get pretty high resolution, but this particular scan does not have that.
We can get really, really small. So 3 microns is the maximum resolution that we're talking about in most cases right now. A CT scanner generates a volumetric model. If you think about pixels brought into 3 dimensions, they're called voxels. So there you go. Generate a model that's made up of millions and millions of voxels. Each of those voxels has an attribute attached, which represents material density. And so we're able to run some scans with voxels as small as 3 microns.
Looking at the traces on the top and bottom of the board, it is quickly apparent that this is an amateur design. For instance, many of these traces are at haphazard angles. It's good design practice to use 0, 45, or 90-degree angles, and most of these are just at whatever angle works. That doesn't necessarily make the difference between a board working and not working. This is more best practice for really high-speed signals. But I don't look at this board and go, wow, I'm extremely proud of the work I did here. When I look at the traces, I notice that most of them are the same size, but all are relatively small. This is a red flag. I had intentions with this board to drive high current servos, and I can tell you by looking at these traces, none of these lines would have supported that super well. The ground pore, or the light blue area that surrounds many of the traces, is also really haphazard here. A larger or more consistent ground pore often makes your board better for RF engineering. Here's some more good routing on the back. The choice to route these signals with this angle is really, I don't know who designed this board, but they did not do a good job. It's me. I designed it. I did it. It's my fault. Sorry. So a CT scanner does have limitations. It's not a perfect device. These red circles are the pins for the power switch on the board. They're very dense. It's very hard for the X-ray machine to see through them. And because of that, they cast these shadows on the left and right during the scan. And we can kind of see that across the whole board. There's this general sense of slightly diagonal, but mostly flat side-to-side motion. And that mostly has to do with the direction the X-rays are traveling. We'll see some artifacts from this later on in the video too. In contrast to the first board, let's take a look at Signal R2. This is the 4th iteration from this version. It was designed about a year later, and I'm a lot more proud of it than I am the old board. The first thing apparent to me about this board is that it's missing the top half of the ground plane up here. In fact, it's a very hard cutoff. The reasoning for this is that right here is the Bluetooth radio. This board was controlled via Bluetooth over an iPhone or Android device, and I needed an antenna to make sure that this could broadcast and receive Bluetooth commands. The antenna sits on the top of the board here, and I didn't want any of the sensitive electronics messing with that antenna signal. Sometimes it's worth putting a ground plane around the antenna, and sometimes that does more harm than good. I am not an RF engineer. I just know what happened to work, and I moved on. Man, it happened again. I'm sorry, you guys. There's this time dilation zone by my house. I've been trying to get it fixed. The repair guide won't show up. It only warps space-time for about a minute each time. So while we're here, let me tell you about the sponsor for today's video, which is Novium. Novium makes this incredible hover pen. This thing floats elegantly at a 23.5-degree angle, which perfectly matches the Earth's tilt. It also gives a really nice writing experience overall. When you're done with the pen, you can put it in the hover mount and it hangs suspended in time and space, much like we are right now. It does this using the closest thing we have to magic on Earth, magnets. Novium's newer release, the Hover Pen Future, comes with a fountain pen tip, and it hangs at a slightly larger angle. They also offer a special edition version of this pen with a real meteorite shard embedded inside. Each pen comes in a variety of colors, so if what you're seeing here doesn't catch your eye, there are lots of other options. If you're looking for an early holiday gift, this might be it. So if you want to give them a shot, you can use code BPS to get 20% off for the first 48 hours only. It's a little bit of an early bird deal. But if you're a little bit of a late bird and you miss that sweet, juicy 20% worm, fret not, my little chickadees, you can get 10% off after that 48-hour period. And also free international shipping to most countries. Links to all these things are in the description down below, and thanks again to Novium for sponsoring this video, and our time dilation field should be just about up. A design philosophy I went with on this board was to keep all passive components on the back of the board and all active components on the front, or most of them at least. This is objectively worse from an electrical engineering perspective, but it is better from a aesthetics perspective, and I was trying to make a very pretty looking board, and I feel like I accomplished that. On the back of the board, we can see things like the SD card slot, the flash chip over here, we can see the pyro terminals down below, and the attachment points for the buzzer. You'll notice that all of these traces follow that 45-degree rule. No trace routes itself at a hard 90-degree angle, at least as far as I can tell. And most traces that don't carry current are very small, while some of the ones that do carry current are much larger. For instance, the traces down here that end up routing current to the pyro channels end up much thicker than the traces that just carry the current signal. The top of the board has this little star field. I really love this design element, and you can actually see it get picked up in the Xray. The CT scanner doesn't detect much of a density change between the silkscreen of the board and the solder mask, but there is a slight density change, which is why we can slightly resolve that little star field up top. What do we think is going on up here, by the way? This area holds a linear voltage regulator, and it's soldered directly to a ground plane. This is obvious in hindsight, but I never thought of it this way. The CT scanner kind of reveals to us that the solder on the bottom of that linear voltage regulator is not consistent. Just like we might have with a bad composite material, we can also have voids in our solder pores. And that happens with this linear voltage regulator as well as with the Bluetooth chip and the main processor here. These two surface mount components have big square ground pores on the bottom of them that helps dissipate heat, and it helps just make sure the chip is grounded. The little bit of solder paste that goes on does not fully coat the board, and I'd never have known that had I not CT scanned it. I'm looking for 90-degree angles. I'm terrified I'm going to find one after confidently saying that they're a problem. I don't see any 90-degree angles, but I do see some real malarkey going on here. The terminal blocks on this board look so strange in the CT scanner because we can't see the plastic. The density difference between the aluminum or the stainless that makes up the terminal blocks on here and the plastic that holds it together is such that we don't see the plastic at all. The density change also lets us see directly inside the flat pack buzzer here and the SD card slot, which is pretty sweet. Maybe I'm showing my ignorance here. Is there a difference between a CT scanner and an X-ray machine, or have I just been referring to it wrong?
Yeah, great question. So usually when you say an X-ray machine, you're talking about a machine that takes two-dimensional X-rays of an object. We take two-dimensional X-rays of an object, but we do it as the object rotates inside the scanner, and that gives us the data that we need to make a 3D model.
Yeah.
So CT stands for computed tomography. The fundamental advance there in the 1970s was the ability to use software to construct these multiple X-ray 2D images into a 3D model.
Now, I couldn't fly with this for reasons that should be obvious, but I also shipped a few rocket motors to Lumafield. I did forget to tell them I was doing this, so a real quick apology to Lumafield. I shipped a box with an explosives label to their office without prior notice, and You know, maybe some better communication could be done in the future on that. This is a Cesaroni I-165 rocket motor. It doesn't have a case. The nozzle is down bottom here and the forward closure is up top. One of the most powerful things to do with CT scanning is the ability to view a slice plane with density information, and that is what we're looking at right here. If you've ever used CAD and done a section view, this is essentially a real-life cross-section without harming the part. In aerospace, we call this NDT, or non-destructive testing. But this is not just any slice plane. This is a revolving slice plane, which means as I take this cursor and I move it around, although it may not look like it, the motor is actually being revolved, or the slice plane is being revolved, depending on how you look at it. So as I rotate back and forth, you can see we have a little bit of off-axisness that has more to do with the scanning technique than the motor itself, but we can start to see some interesting things. First, I want to point out at the very bottom of the motor, you can see the reflection lines change. That's because we scanned the motor at a slight angle instead of directly upright. We can get a little more interesting detail by doing it this way. Second, you can see that as I move back and forth, we get these little voids in the forward closure. This is very interesting to me because the forward closure and the nozzle are pretty important parts, so to have voids in that is probably not great. I am not a commercial motor designer. Maybe this is totally fine. Maybe this is just a normal manufacturing thing. That said, I was expecting to see more voids in the propellant and less voids in the closure. And for what it's worth, I do not see any voids in the propellant. What I can see here is the starter grain. This is a little bit of black powder or pyrodex that goes at the very top of the motor. Ammonium perchlorate propellant is actually fairly hard to light. Now, I'm not encouraging you to just try with a match, but it requires a little bit of heat and a little bit of pressure to get going. So most of these motors come with a little starter pellet that's at the top of the motor, and if you ever read the instructions for these, you'll see they want you to put the igniter all the way into the top of the motor, and that's why you're lighting the starter grain, which then lights the rest of the grain. In terms of basic components, we have the nozzle carrier, the grain, the starter grain, the delay grain, the black powder, the forward closure, and the O-rings. From this view, we can slice the plane through the motor sequentially from bottom to top. This is the nozzle opening up, and now we're looking at the propellant grain cross-section. This is fairly consistent, as I said before, basically no voids, and now we've got that starter grain. Finally here, we hit the delay grain, and then right before we hit the top, we get to these huge voids. So these turn out to be much bigger than I initially imagined. Again, I'm not making these motors, but I do find these voids to be surprisingly large. So that's a rocket motor using ammonium perchlorate composite propellant, a thing that we have talked about 1 billion million times on this channel. But with smaller hobby motors, we can also use black powder propellant. Black powder is much less dense, but it's a little easier to light and it has a lot more heritage in model rockets than APCP. If you've flown a hobby store rocket in the park as a kid, it was probably on a black powder motor. This specifically is a C65 motor, but I also brought a C12 to Lumafield. The C12 is really comparable to the C65 in terms of total impulse, but the propellant of that motor is ammonium perchlorate composite propellant, so we get to see how these two very similar performing motors are fabricated entirely differently. We scanned these motors at a slight angle, just like last time, to help the CT scanner, and we did both of them at the same time. You're looking at the raw projection here, and it sort of shows why it's better to have some tool that does post-processing for you. I can scrub through this and certainly learn a little bit about the motor, but it's way nicer to have this image which is processed to show density much better. This is the C12 ammonium perchlorate composite propellant motor. We can see how this forward closure is retained with these threads right here and an O-ring to seal against the case. The nozzle presumably does not need an O-ring because the motor operates at a lower pressure in this region, but also this nozzle seems to be cast into the case itself. Scrubbing through the part from top to bottom, starting at the forward closure, we can see the threads as they swirl around the outside of the case. We can see that black powder and then delay grain. Then we reach the fuel grain, which opens up and has some inconsistencies in it, but is overall pretty good. Then we have the rest of the chamber, the nozzle, and the end of the motor. The C65, which is the black powder propellant comparable version, tells a much different story. Both the nozzle and the cap on top are made of compressed clay, and the entire volume is filled with this black powder propellant. This motor is what's referred to as an end burner, and although there's a small core at the very start to get the rocket to kick off the pad, for the most part the grain recedes in a flat fashion. This part is a little tricky to see, but it's easier if I move back and forth. We can see two sort of puck-looking figures here as I circle through the motor. These are the delay grains for the C6.5. The C6 comes in several different delay variations, and immediate deployment, 3 seconds, 5 seconds, and 7 seconds. We can see how Estes does this through the magic of CT scanning, which is presumably by adding these little pucks into the top of the motor. And if I had to guess, these pucks probably represent like 2.2 seconds of delay each. As we scan through the nozzle on the right, we can see the density of that clay. This is just a compressed clay nozzle. They're very, very simple to make. I think Estes has like a whole patented process for how they do it. And then it's easy to see the density change as we get to the black powder propellant. This propellant has some inclusions, like whatever this is going on here is probably not a normal part of the propellant. And then in contrast to the large grain black powder propellant, we can kind of see a transition to the smaller grain delay. This stuff is kind of difficult to show in video, which is why I have great news for you. If you are enjoying these scans and you want to poke through them yourself, they are in the description. Like, you can go look at these right now for free. Again, Lumafield did not sponsor this video. They did fly me up, but they did not tell me what I couldn't say. But I'll just tell you, it is really cool to poke through these things, and I recommend giving it a shot. I heard from Austin that it is actually safer to stand close to the CT machine when it's on than it is to stand elsewhere. Is that true?
That's right, yeah. These machines are full of lead. They literally have a ton of lead in each machine.
Yeah.
That shields all of the X-ray radiation that we're generating from the X-ray source, but that much lead can also block the sort of ambient background X-ray radiation that's all around us, which comes from the rocks in the soil, it comes from the sun, it comes from other sources of radiation. And when you stand next to one of these machines, there's so much lead next to you that sometimes the radiation reading is actually lower than it is if you're not standing next to the machine.
There you go. It's super safe. It's safer than everywhere else.
You can't afford not to have one of these in your pocket. So.
Okay, 2 more things I want to look at here. This is the fin can for EBDB1. These are the fins that took a right turn at Mach 3. Yikes. And one of the fins is a little worse for the wear. This happened on the second flight of EBDB, which I haven't made a video about. Maybe this is a good video to make in November. I'm thinking of doing a no-effort November. Let me know if you'd like a couple of no-effort videos in November. Anyway, what you need to know is that when EBDB2 launched, Ava took a nap and the stage came in ballistic. When it hit the ground, the fins snapped like this, and this gives us a cool opportunity to see the failure mode in the CT scanner. Before we look at the X-ray, let me show you what this should look like using Onshape. With composite fins like this, we're basically looking at 4 parts: the airframe, the epoxy fillet, the fin itself, and then the fiberglass layup on top. All these parts are supposed to work together to keep the fin attached, and they usually do pretty well. They just don't do so well when you slam it into the ground really hard. We'll start with the raw projection, and you can already see some problems. In the fillets of the fins, you can see a lot of tiny little bubbles. I used fairly thick epoxy, and I was not able to degas the entire set of fins, so these bubbles are just an application issue. We scanned the whole set of fins, but Lumafield software Voyager allows you to do different regions of interest. This is notated as ROI, and you can see ROI2 is the region of interest that specifically surrounds the broken fin. Using density to represent color, you can see the different parts of the broken fin. We have the 1/8 inch base plate of carbon fiber, the bent and then broken fiberglass layers, and then if you look close on the inside, you can see the fillets here. Okay, I think this next way is a really cool way to do it too. This is scrubbing from the top down through the fin. As I move down through the top of the fin, we can see with much more specificity things like these massive voids on the inside of the fillet. But what's interesting to me is that it's not failing necessarily at this void. Apparently, we can have a little void as a treat. What did really fail is this surface right here against the fin itself, and this delaminated off of the base fiberglass. As I scrub through, you can see that this is a mostly consistent failure, but not through the whole fin. At some point, we do have some epoxy that remained on the surface of the fiberglass base, though it's still delaminated from the carbon fiber fin. Scrubbing through the whole thing, it gets kind of messy. There's little bits of debris in there. This thing had to like go through TSA and also live for about 1.5 years before it got into the CT scanner. Another cool tool in this software is crack detection. So while it's very clear to me that this fin is like capital B broken, because of the way composites work, we know that there are probably more cracks in here somewhere. If you're just looking at this raw projection, you might not be able to spot them super well, which is why Lumafield actually has a tool that allows you to look for cracks specifically. It's a little hard to read this if you don't know what you're looking at, but essentially we're highlighting any bubbles or areas where there's clear crack detection. To make it very obvious, this is an extremely broken fin, but would you have bet that this section is also broken? Or that there's some delamination around around here, or that there's like a subtle bit of cracking right here. We can see areas like this and like this where my epoxy didn't coat super well, or that the fiberglass layup didn't stick to the surface super well, and sections like this up here where the fiberglass is completely delaminated, even though this section still looks like it's mostly attached. The last thing I wanted to take a look at here was these phenolic rounds. I bought about 14 of these last summer because that was the minimum run for a custom order. These were not cheap, but boy, they make really good rocket nozzles. I got this custom run from a company called Bodecker Plastics, and they were about $220 a piece. But when I was ordering them, Bodecker was not stoked about making the roll this thick. They said that anything above a ½ inch thickness of phenolic was at risk of cracking. This was a big concern for me, one, because it was a big expensive order, and two, because I might not know about that cracking until it was time to actually make a nozzle. Then halfway through manufacturing, I might be turning it on the lathe, and it turns out my stock material is inherently flawed. So I brought a roll up to Lumafield, and we tossed it in the CT scanner and left it in there for a while. Here's the raw projection of the phenolic round. You can actually see the fixture. We held it on here, just a little bit of styrofoam. And like before, the raw projection tells us a little bit, but not too much. But once these scans get processed, we can use tools like slicing through it to make sure there are no issues. Using a sliding slice plane in the horizontal axis and an up and down slice plane on the up and down axis, I do not see a single crack or a single void in this material. This is great news. This means that more than likely all of the phenolic rounds I ordered are of this quality, and I did not need to worry about cracking that much. Industrial CT scanning is really cool. I was super excited to work with Lumafield on this, and again, they did not sponsor this video. They did not get to review what I say here, but I had a great time visiting, and it was really cool of them to let me toss a bunch of things in the scanner and see what comes out. I really enjoy nerding out on this stuff, and if you're watching this, you clearly do too. I'll be back here with quite a bit more content by the end of the year, so make sure you're subscribed. Thanks a ton to Lumafield for letting me tour their offices. Thanks to you for watching. Thank you to the patrons who also support this project. And if you want to see what I'm doing in real time, there's updates every 2 weeks there. My name is Joe Barnard. May your skies be blue and your winds be low. Goodbye.